really great pleasure to have Professor Vanderlei Bagnato, today's PQSEI speaker. Vanderlei is a distinguished physicist, professor in Brazil, one of the campus in Sao Paulo, the Sao Paulos, okay. And he has made many contributions in many different areas in generally AMO physics, optics, from boson condensation, cold atom collisions, to even biophotonics. He's running a big center in Brazil, working on many aspects of the AMO physics, optics, and he has received many awards in his career. I won't read all of them, but he is an elected member of both the National Academy of Science in the US and of course Brazil and various other countries. So I think without further ado, I will turn to him. It's really, again, a great pleasure to have you here. Thank you so much for giving today's talk. And hopefully one day we'll have you on campus to have an in-person interaction with us. But I think at least we'll have a nice online event today.
No, I'm the one that should thank you for inviting me. It's been more than a year now that we are isolated, personally, physically speaking, right? And it's very important for us to make connections, to be able to open up, like the horizon of cooperations and ideas and everything. So I appreciate very much. We had a previous conversation before. You gave me a full seminar about the collision of two condensates. So that was very nice. And we have a sequence of conversation with people that some of them I know already, and some of them I know from names. So it would be very nice. Okay, so I'm going to share the screen again and give you the seminar. And you can interrupt me anytime, because if you feel very bad with the question, don't wait till the end, you can ask me. So what I'm going to show to you is some experiments we have. I am in this building here that you see is a Institute of Physics in São Carlos, University of São Paulo. We have a large group. I'm going to show the picture at the end. We have 4 laboratories of cold atoms. We have my laboratory, which basically is doing condensation. We have the atomic clock lab. We have the laboratory of Philippe Courtel that's doing scattering of light, cooperative scattering and things. And we have the laboratory of Emmanuel, which is doing dysprosium condensate. And in my laboratory for the last 10 years, I would say, I've been trying to concentrate in study excited condensate, like taking the condensate out of equilibrium and try to see what we're producing and how it thermalizes and how can we use that kind of system. And one of the things that we've been doing since 2010 basically is the turbulence. By exciting the condensate, condensate is a superfluid, so we can try to produce turbulence out of it, like they do in helium. So that was the idea in 2009, and since then I've been kind of elaborating this idea. And to introduce turbulence, turbulence is all around us, but it still is an open problem, either in the quantum sense and in the classical sense is even worse. People believe that when we go to quantum fluids, we could do easier understand, because as you know, in the classical fluid, there is no quantization of the angular momentum, so vortices can be anything. But in the superfluid, we have a quantized vortices, so that looks like filaments that can be better treated. So the hope is that we could understand a little better the situation in the quantum fluids. Okay, well, just to tell you a little bit about turbulence in general, there are a few requirements when you're doing turbulence. And the requirements are that you need some randomness, right? Unpredictable sensitivity to initial condition. Depends how you start, tiny little change will change completely the outcome. You need some dissipation because the energy will be introduced in some scale and it must dissipate. In the case of normal fluids, you have viscosity. In the case of superfluids, you have a few mechanisms that produce the dissipation as well. You need a cascade, which means you introduce energy in one scale, normally large scale, which means low momentum, and that cascade down in scale and in increasing of momentum. And you must have some scaling on the properties of your system. And the most famous one is the Kolmogorov type of scaling you do because of invariance. And you can find out that the energy spectrum, it has a power law. There is a range of momentum where the energy obeys a power law, which in this case is the -530 laws. That is Kolmogorov, and people have been showing that this is present in many turbulence phenomena using classical conditions, using classical fluids. And this is kind of thing we look for the quantum. Well, in the quantum fluid, turbulence is being introduced long ago. And if you produce vortices, it's possible that those vortices line, they cross each other and they having those connections. And they produce wiggles on the vortex line because you have two lines as you see in the picture, and they cross and they became banded. And if you can imagine many crosses like this, you're gonna have rings, you're gonna have wiggles on the vortices, and sooner you're gonna have, because of this, a tangle configuration of vortices everywhere that is classified as a turbulent regime. There are a few types of turbulent regime. One that's fully with vortices, and the other one is with waves on the condensate, density waves in the condensate that normally we refer as wave turbulence in the condensate. So those two types are the ones that we try to investigate in your condensate. Well, as I told you, when we produce vortices in the condensate, they may cluster together, making bundles. So then many quantum vortices together will look like classical vortices. And this is what people observe in liquid helium, big tanks of liquid helium, where they produce vortices by shaking wires. And they see those vortices bundled together. And then they behave very well and they produce turbulence as well. But there is another type that's called super quantum, which is basically you have a vortices line you produce and they react, they produce this kind of tangle configuration of vortices without bundles, but you know, a big mass of rotation fields everywhere. And that's Vinning, from England, he proposed and he first worked on this kind of turbulence in liquid helium. And they normally call Vinning turbulence or superquantum. And then you may have the wave turbulence as well. That's something that is present in the superfluids, because if you produce waves, those waves, they have a nonlinear interaction and they can produce a big mass too, which has all the characteristics of turbulence. So normally we work with these three types. I am mostly in the second and in the third one, as I'm gonna show to you.
I have a quick question.
Yeah, please.
So when you speak of turbulence in superfluids, what are you starting from some kind of constitutive equations for the conserved quantities, or are you looking at it from a more observational standpoint in the way you presented in the last slide, which is that you're just going to look at vortices and perhaps their dynamics
Well,
and statistics.
I start with a pure condensate. This is a full experimental talk, okay? Of course, I mean, we follow some of the theory and we use theory to explain a few things. So normally I start with a condensate and I'm going to excite and I'm going to show to you how I do. So I'm just give you the general picture of the quantum turbulence people refer to.
I see. Thank you.
Well,
so normally what are the important Yes?
Okay. Well, okay. Are you going to focus on 3-dimensional condensates or 2D?
No,
well,
3-dimensional.
Okay, so these vortex lines are certainly relevant to excitations in 3D. But in 2D, is the thing we don't have we only have vortices, not vortex lines.
Yeah, that's right. In the 2D will be different, and the behavior will be different, and the cascade is invert. So many things is different in 2D. I'm talking about general ideas in 3D.
Thanks.
Okay. So the main aspects we have to remember, and I think for these audiences, I'm not going to lose any time on this, is that the circulation, if you introduce rotation in the superfluid, you have quantized the angular momentum for each atom, which means that the circulation, the integral of the velocity field around the line is an integer number of h divided by m being the mass of the atom. And this integer number, which is the n here, if it is 1, we call a single charge vortices. If it is larger than 1, we call a highly charged vortices. And normally there are unstable vortices. The 1 is the one that's stable. The vortex in the superfluid, it has a core that's the healing length, as you know. And people has been producing vortices, and if you just rotate the condensate, suddenly you make many vortices, and because a vortex of a circulation 2 is not stable, it can decay to 2 of circulation 1. And what you do is you make a lattice of vortices, and it's like a Brikosov type of lattice, and people has been investigating that too. I don't go to the regularity, I go to the disorder. So my experiments are, I have 2 experiments in this field. One with the rubidium atoms that we produce is from single vortices to a big mass to the turbulence. And we have another one with the sodium and potassium, where I was trying to produce lattices of vortices, as you can see in the sodium condensate, and fill it up with potassium. So those are some of the experiments we're doing. Try to put mass inside the vortex, because if there are repulsive, you know that the vortex will work like an attractive spot for the second species. And then we're doing some experiment in both of these systems, even though I'm going to concentrate in some experiments I'm doing with the rubidium. But we can talk about the sodium and sodium potassium later. This is a main feature of those turbulences. Normally, you inject the energy by somehow you inject energy at the high, at large scale, and then as I told you, they may react, those vortices may reconnect it, and then you start to put the energy down, like in rings, and this is called Richardson type of cascade, or you may produce wiggles by these reconnections, as I told you, and this is called Kelvin wave cascade. And the energy goes down then, because of originally you had only the rotation, now you have all these wiggles in the vortices, and eventually you reach the dimension of the atoms, and then you have phonons with actually the sound wave production works like dissipation in the system. So this normally will take place in the cascade. Will almost always take place in those superfluids when we excite. How I excite the system? Well, I call this a washing machine. atomic washing machine for the atoms. What I do is I introduce tiny deformations and tiny rotations on the potential. So mainly by putting extra coils out of the axis, I can squeeze the condensate, not regularly in different positions, and also produce tiny rotations. And if I do that in the right way, with the right amplitude, with the right frequency, I start to generate vortices. Normally, I made some studies. They normally generate on the boards and migrate in, but this is not the important thing here. And when I saturate my sample with vortices, I wait a little bit and they evolve to a very messy type of configuration, which we believe is the turbulence, and then we go to characterize. So a time sequence, what I do with my sample, my condensate, in this case, the rubidium atoms, about 10 to the 5 atoms, you know, like 1 million atoms in order of magnitude in the condensate. And I produce those excitations. So I produce the condensate, then I excite with this oscillatory mechanical effect, which is not fully rotation. It's like a washing machine, right? It goes in both directions, and that's enough to transfer the angular momentum to generate vortices and anti-vortices. And we don't do that in only one direction because those coils are off axis. Actually, you're shaking the condensate in many directions, and then you produce vortices in many directions. So in this picture, you see a few vortices and then the evolution to the condensate. Normally, that's how the profile after time of flight and observation looks like. We produce individual vortices or many vortices, and then we see the evolution to this very fluctuating density with many vortices present. Normally, after you produce the turbulence, you cannot identify very well the vortices. And if you keep putting energy, we go to another state that we call granulation, but we are now investigating this in a different context. Okay. Normally, the parameters that I can control in my experiment is the amplitude of the excitation, is the time of excitation, and the frequency of excitation. For the work I'm going to show you from now on, I fixed the frequency for some frequency of excitation, and I'm investigating what's happened when I change the amplitude and the time of excitation. And what we observe is for small amplitudes, we observe the bending mode that you already know, that's traditional for the superfluid, was investigated by Chris Flute long ago. And then we see the vortices being formed, and then we see the evolution to what we call turbulence, and then we're going to characterize this regime. And if we keep pumping energy, we go to some other state that we are still investigating what it is, and we call granulation because it looks like domains of condensate that we have in the sample after that. And this work has been simulated by 2 different theoreticians, Yukalov in Dubina and Tsubota in Osaka City University. And they all
what is the horizontal axis in the big plot?
Oh, I'm sorry. I think the transparency is the time of excitation in milliseconds.
I see. Thank you. Thank you.
And the amplitude, I plot here in milligauss per centimeter, but normally we express in terms of the chemical potential, okay?
I see, thank you.
Based on how much energy we transfer. Normally what we observe is we see the vortices forming, and then suddenly we cannot recognize any more vortices, and then if we count the number of vortices, we see the number evolving, like growing to some number that's not very much because our sample is not very big. So you can imagine that very soon you saturate with vortices your condensate. You have no more space, and any further energy forces the vortices to react. And then, I mean, we see we don't identify the vortices anymore, and then the number decay. One of the things that's very common in working with this kind of physics with the turbulence is to evaluate the energy spectrum, because the energy spectrum will show to you important features, including what they call the inertial range, which is a range of momentum in which the energy flows from large to small scale. And this is one of the requirements for having the turbulence, is having presence of the cascade. And then the things we've been working is find out the spectrum. And we do that in two different ways. We measure the momentum distribution by time of flight, because now we have a sample that's basically kinetic dominated. It's not anymore a Thomas Fermi type of profile, because you introduce all this rotation in there. And we've been evaluating this together with some theoreticians that you know, like Alex Fetter and many others that collaborate with us, or even Gordon Bain. And we assuming that we have a very nice kinetic dominated sample, by expansion, by free expansion, we can evaluate the momentum distribution, the population in each momentum class. And because it's kinetic dominated, the integral with k squared with the momentum distribution give you the spectrum of energy, give you the energy that is contained in each momentum class. But we do in a different way too. We use power spectrum. Power spectrum is a kind of, you do many shots of the same conditions, and then you do a correlation of the density fluctuation. And then we use the Fourier transform, and you basically get the power spectrum. So this is using the Wiener-Quintini theorem that's very useful in many fields of physics to evaluate power spectrum. When we do the time of flight, basically you let the condensate to expand, and you see how many atoms have a different momentum, is belonging to some momentum classes. And we do that by doing time of flight and absorption, so we are projecting. And then we do an approximation that's using the Abel transformation to try to recover the three-dimensional momentum distribution, assuming that that's isotropic distributed. We do that, and then we have N of K, which is the momentum population. How many atoms are with momentum between K and K plus dk. And when we do that, if we have a few momentum, we don't see the big variation. But when we are in the turbulent regime, we clearly see the distribution, and we see a range of momentum which has a power law, in this case with -3 exponent. We have done this some time ago. Like in 2014, we have been playing with this momentum power law. But, and then if you do the power law, you get the spectrum, the way I told you. But we can do as well the power spectrum by taking many shots, doing the subtracting the average density profile. You end with the fluctuations, and then you do correlation. And then from that correlation, you do the Fourier transform. And that is a well-established theory that show you that you are getting the power spectrum. And then we do that as a function of the amplitude. So you see different power distribute energy, the power spectrum now for different situations. And you can see very clear when the kind of anomalous behavior is present. First of all, allowing more atoms to go to higher momentum, and the presence. If you put in a log scale, you see clear the power spectrum appear in the inertial range, which is not a big range because we don't have in this situation, a big range of scales. So we see a little bit. And then from both methods, we compare, and always that the turbulence appear is where our approximation is valid. And we see that both exponent present in the energy spectrum coincide. So actually we see energy spectrum that goes with -1 in both cases. And that's compatible with either a tangle configuration of vortices predicted by Vianney, or a wave turbulence, or maybe a composition of both, because the way I excite, we don't exclude that maybe we start with one, seeing the vortices being generated, but this evolve later to a kind of a wave turbulence. We've been we've been studying the presence of isotropic versus non-isotropic behavior. And it's very interesting because even if the cloud is not isotropic, we see the same behavior, right, in different ranges, because now we have different scales in each direction to play with. And but we see the same loss in both directions, I would say. So, and this question of isotropy on the turbulence is still open for us, and we are still dealing with this now at the present moment, investigating in what range we see isotropia and in what range we see complete non-isotropic type of behavior. Well, to close the picture, you have to show energy flux in some range, because this is what characterizes the cascade, is the energy flowing from large to small scale, or from small momentum to large momentum. And we've been able to characterize this by analyzing the power spectrum and the time evolution of the power spectrum. We are able to extract the flux of energy flowing from the momentum classes. This is a paper we published last year in the Europhysics Letters, where we were actually able to show the flux by measuring different energy spectrum in different time, by holding time, different holding times, so waiting different evolution of the energy from the different scales, the different momentum classes. And we are able to show that there is a range of momentum where the flux is constant, where you preserve the flux. So energy that gets in one momentum class will leave in some further momentum class, which characterize is another way to look to the cascade. And also we've been evaluating some parameters like disorder, right? So we measure the entropy in two different ways. I'm instead of explaining detail, I was going to invite you to see this paper that we published beginning of this year, in fact, showing that actually when we reach the turbulence, the system really evolved to a large entropy. And there are other things that we could characterize in the system, showing that the disorder is actually established. Recently, we've been measuring what we call the integral scale length. This is more or less how the energy migrates in scales. And depending on the amplitude we excite here, I fixed the time of excitation, I vary the amplitude and the holding time for each amplitude. So I excite for a finite time interval, and then I wait for different times interval to see the evolution of the non-equilibrium distribution of energy that I produce. And people in regular turbulence, they work with this quantity that they call integral scale length. That basically tells you where is the energy going, where is the mostly scale, where is the scale where the energy is mostly concentrated. And as you can see, small amplitudes do not change very much. a change with the time, but not the way when we reach turbulence. That's about in the middle here. If you see the scale, is where we are on the order of 0.4, 0.5 mu0, the chemical potential of amplitude of excitation. Then the things change completely, and the behavior of the flow of the energy in the spatial scale, it goes with the time. And sorry that I put my whole hand plot, but I like to do this, and it shows that actually the energy is going down, and we will reach a very small scale, where then is the end of the turbulence. Is when you reach a small scale, is that will be the dissipation, final dissipation, and then you lose the turbulence, and you end with a lot of thermal excitations. Okay, so what I gave up to now is a kind of overall idea what we've been characterizing in this turbulent cloud. And of course, I was very fast, but the idea was to show some of the measurements we can do to actually try to be safe that we have a kind of turbulent cloud. But now I want to apply the turbulent cloud. I want to do some studies with it. And I've been taking 3 pathways. The one pathway is looking to this turbulent cloud as a matter wave with the random amplitudes and phases, which is somehow characterize what we call speckle of matter waves. You know, remember the speckle of laser, where we scatter the laser in a surface, and then we have random amplitudes and phases. Here we can produce that with the matter waves that originates on the turbulence. So basically, this is an expanding cloud that will have all the characteristics of a 3-dimensional matter wave with speckle field. And I will show you the experiment where we compare both. I used to say that a turbulent BC, you know, we always make the analogy that a BC is for atoms what a laser is for light. And now I want to add that a turbulent BC is for atoms what a speckle laser field propagating is for light. And then there is also the universality behavior when we are far from equilibrium. This is a non-equilibrium sample. It's a quantum fluid out of equilibrium, and we want to look for universality classes depending on all the theory people are doing, and I want to explain to you. And I did some experiment. We have to do more on this Anderson localization, dynamical Anderson localization for the high class momentum atoms interacting with the turbulent core, which is the superfluid. Okay.
A quick question.
Yes.
In the turbulent regime, are the quantum effects of quantization of vortices still important in your experiments?
Well, you see, the turbulent is quantization is always important, but after you have so many reactions of those vortices, I cannot identify anymore. You know, I see the vortices in the very beginning of the excitation. After that, it's very hard for us to see because they react, and all this energy went to so small scale that maybe I lost the identity of those vortices.
So I'm trying to understand. So I'm a condensed matter physicist. Just to explain where I'm coming from, what aspect of the BEC, the fact that it's got a order parameter which depends on breaking of the global phase symmetry, where does that come in the turbulence picture? By that time, is it effectively just a normal fluid with only mass conservation, mass and momentum conservation?
Yeah, energy and number conservation is present. Now, the order parameter is a characteristic of the equilibrium BEC. So if you wait long enough, this system will recover a BEC probably in different temperature with different fraction in the condensate.
I see. Okay, thank you. That clarifies a lot.
Yeah, but that's when we decay. now we are dealing with a non-equilibrium BC. So you see, I have a I have a quantum fluid, but it's not like the equilibrium BC that we are used to start with. That's our starting point. Up to some level, I still preserve. You see this sequence of pictures here.
Yes.
You can clearly see that after some excitation, we still preserve all the order parameter and everything until the point where these start to react and the disorder is installed.
Okay.
And then the system is out of equilibrium, as I'm going to show you. Okay.
Okay.
Right. Okay. There are some characteristics of the turbulent BC that I should show to you. We all know that if you have a thermal gas, doesn't matter the shape, when you let it expand in free space, it goes isotropically, right? After a while, it goes isotropically. If you have a BC, and in fact, this is one of the fingerprints of BC, when you let it free expanded, where the dimension that was more squeezed in the original in situ situation will expand there faster, and you have what we call the inversion ratio. Those are characteristics of the BC, regular BC, which is fully equivalent to a laser propagating, right? If you have an elliptical laser profile, Gaussian but elliptical laser profile, it will diverge. It will diffract more in the shorter dimension. We know that. Now, when you have a turbulent cloud, that doesn't happen. You know, it seems that expanding in a self-similar way, it preserves, after some time, it preserves the aspect ratio. And this is a very interesting characteristic. This is showing to us that we don't have either a thermal, neither a fully both condensating equilibrium, as the colleague was questioning me about. So this self-similar, we have the, yes.
Vanderlei, if you have a turbulent thermal gas, I don't know if you can talk that way, how would that expand?
Oh no, that we'll do isotropically as well.
Okay.
You know, because the thermal, first of all, we cannot hold the turbulence too much. It dissipates very, very fast. But suppose that we can make a big disturbance of the Maxwell-Boltzmann distribution in a gas, you know, you just go to another temperature, we will expand, and after a while, we will go isotropic as well. It still be a classical gas expanding. And we've been doing this on the board limit, try to produce very large, you know, in fact, everything we observe only happens when you have a fraction condensate. If you try to do all excitations I told you before, you just shake a little bit the cloud and everything, but no vortices, anything, right? You cannot nucleate the vortices the way I do in a thermal cloud. It's only, you needed a condensate there to be able to accommodate. Maybe if you're steering with a spoon, a laser spoon, you could produce a big vortex that will decay like the water in your sink. Okay, then what I did some studies is comparing the matter wave propagating in space, which is what's happening in free expansion, with a speckle field. Here, what you see is a regular condensate in expansion that looks very much like a laser in propagation. As you know, that is the inversion ratio, and it propagates. Now, when we have the turbulent cloud, a good question is, when you are like, you are perturbed, you have vortices everywhere, but you are not turbulent, then we disturb a lot the propagation, but not to this limit. And well, so when is a turbulent, you see the different regime, as I told you. And then what I did is compare this with a speckle field of light. If you produce a speckle in a laser field, which is characterized by a collection of random amplitudes and phases everywhere, it has equivalent behavior. When a speckle field propagates in space, it do not diverge. And I'm going to explain you why. And that's equivalent to what's happened in the turbulent cloud. And then I did.
Can I ask a question?
Yeah, of course.
So with the laser speckle, you require some disorder that the light can scatter from. In this turbulent case, do you have any disorder, or it just all comes from the liquid itself?
It's fully disordered because we produce so many vortices that at the end of the day, after they react, what we have is a big fluctuation of intensity and phase everywhere. Okay,
but there is no disorder in the potential, or?
No. Okay. It's everything is in the fluid, is in the cloud.
Okay, thanks.
The potential is there now, just holding it's like a cavity for the photons. The potential is holding that matter wave with disorder everywhere there.
Okay, thanks.
Okay. Now, this is just for you. I know that you guys are very mature physicists, but when you have a coherent laser field and you let it propagate, you know that the angle of divergence depends on the wavelength and the waist. But when you have a speckle, the angle of divergence is the wavelength divided by the coherent length, or the correlation length, I'm sorry. The correlation length basically will be related to this, to the size, to the domains of this speckle. And therefore, this, you see, this angle is different from that one. That one preserves the divergence following the geometry of your sample. This other one, no, this only depending on the size of the domains here you have, because the divergence will be given by that. So I made the experiments to show a full equivalence between the BC and the optical beam propagating, either in a regular BC and a regular coherent Gaussian laser beam, and a turbulent cloud and a speckle laser field. And you see it's very equivalent. And then we went a little further doing the density correlation to find the, you know, the correlation length and everything. So this is the atomic cloud. What you see in red is a turbulent cloud, and in the right side is the speckle light beam, the light beam with speckle, and in green is the conventional BEC and the regular Gaussian beam propagating, and then we characterize it to make sure that everything was going well. And the idea here is that you have the domains when you have this, and those domains with preserve all the coherence, everything, they expand following the idea of the original condensate. But they if you imagine this growing, each domain is growing, preserving the shape. So physically, that's what's happened, and that's what's happened with the turbulent cloud and the the speckle in a laser beam. So what I try to prove with that experiment is that, well, this is a demonstration. I like to say that this is an experiment that allows you to put inside the statistical quantum turbulence, which I could merge quantum turbulence with statistical atom optics. You know, in statistical atom light optics, people deal a lot with this speckle field and everything, do the statistics and everything. But here, I'm doing now with matter waves. And then I think this was a very nice demonstration of speckle of matter waves in 3D. As you know, there are many applications of light speckle, right? Light speckle spectroscopy is something very important to do Dopplermetry, to measure velocity of things and everything. I don't have yet a good application for the matter wave speckle 3D, but I think people can find that out, good applications. So this is what I add is a BC is like a laser, while the turbulent BC in expansion is like a speckle laser field. Okay, now there is another thing that we were originally thinking about doing. The speckle came around, which is the study the non-equilibrium BC, the non-equilibrium quantum system. So when we do the turbulence, clear we have a non-thermal state, and the way we observe this is by looking the density profile, which is associated in expansion with normally a regular BC will have a Gaussian tail, which is the way we do the thermometry, the way we take the temperature. But when you have the turbulent BC, of course, we cannot define temperature. It's fully out of equilibrium. We have an exponential type of profile. We migrate from a Gaussian to an exponential. And as you know, exponential profile in this sense is a characterization of a non-thermal state. Which, I mean, many people in turbulence will say, well, that's obvious, but was not so obvious to us. And then we did the experiments showing that actually there is a non-thermal state present. And just to clarify to you, this is a plot of the momentum distribution, and then normally we characterize the power law in this blue range. We characterize the turbulence, but now we are going much further down, at least one or more orders of magnitude in the number in the population. So we are in the red part, right, where we are looking for the behavior, which is these higher momentum atoms that normally in an equilibrium situation, we show a Gaussian type of dependence. And now we see an exponential. And what's very interesting, we see that when you reach turbulence, we go from the Gaussian to the exponential. So I don't remember exactly the colleague that asked me the question about how is the things going. So here you can see that as I excite, I fix the time of excitation, and I excite with different amplitude. Up to some point, I still could say that I have a nice thermal state because it's a Gaussian. But after that, I go to a exponential type of behavior, which characterizes this non-thermal state. And if you have a non-thermal state, it's nice to see how that evolves in time, because this is a kind of very interesting and very, let's say, actual or in the present time interest of physics to know how out of equilibrium or far from equilibrium system evolve in time. And this is exactly what I'm doing. I'm producing a system that's fully out of equilibrium, and I can see the evolution in time. Well, 2 years ago, there was a sequence of papers in Nature showing that how those far from equilibrium systems evolve in time. And they took these systems out of equilibrium by quenching, by many different ways. And those non-equilibrium systems, it seems that many of them, they have what they call a non-thermal fixed point. Even though the system is far in equilibrium, you start, the system is evolving, but if you have those non-thermal fixed points, it seems that the system hang around, and around that non-thermal fixed points, the non-equilibrium system evolving following very specific scaling laws. And that scaling is fully characterized by exponents. And then depending on the exponents, we say that this system belongs to some universality class. And there are many theoreticians around the world that works with this, and this is not fully new. I mean, it's more than a decade of studies to try to understand the evolution of those far from equilibrium quantum systems. And what I did is just see if the turbulence belong to those class. If actually the turbulent cloud and the time evolution has some range of time and momentum where we could characterize by being on the neighborhood of one of those fixed, non-thermal fixed points. So what I do then, I start with my momentum distribution, always doing the same initial condition here. But we can vary the initial condition too. But what I'm going to show to you is I'm varying the amplitude, of the excitation. And for each amplitude, I'm going to evolve in time the distribution and observe how that goes with the holding time, with the time that I'm waiting this quiet without adding any more things, without adding excitation or to excite. Okay, so this is a sequence for one specific amplitude. I'm sorry, I did not put the amplitude here. How the momentum distribution evolves in time when I excite. And then there is some conditions to energy. The energy will grow in a specific way, and the number should be more or less constant in the time window that this kind of scaling should be valid. So what I did is I look for situations where my momentum grow with k with the time square the way you see here, and the number more or less preserved constant within that momentum class. And then if we are on the neighborhood of a non-fixed thermal point, this whole function should evolve in amplitude and in momentum. So as you can see, I'm doing a scaling of the momentum and the amplitude. Alpha is the coefficient, is the exponent, for the evolution of the amplitude, while beta is the exponent for the evolution of the momentum, right? So this is a scaling transformation. And by doing this transformation, if we have all the plots in a universal plot, means that is an indication that they are around one of those non-fixed thermal point, non-thermal fixed points. And alpha and beta has a relation. The theory shows that the relation is the dimension of the system. So those are plots of different waiting times of our experiment. And when I apply the transformation, I can make it in some intervals of momentum and in some windows of time to show that everything collapses in a universal plot, showing that probably the turbulence is one of those phenomena that time evolution may be related to the existence of those points, right? Even though the system is out of equilibrium, it evolves in time following a very specific scaling law. And then we relate to the alpha and beta to make sure that this is consistent with the dimension of our system, which is 3D. And those are also another collection of plots showing to you that when we do the rescaling, we actually make everything agrees. What is T0 in this scaling is one of the reference time. I normally choose either the longest waiting time or the shortest, but doesn't matter. You can choose any one that scales the same way when you do that. Well, so I think with this experiment that the last one I showed to you, we're starting to show evidences that quantum turbulence in those condensates, at least, they show the presence of non-thermal fixed points. And that allow us to maybe understand a little better what's going on in this non-equilibrium regime. And I think the turbulence on the Bose condensate, originally we said, well, maybe we can understand the phenomenon of turbulence. Right now, I think we can produce a very nice and out of equilibrium or far from equilibrium quantum system that allow us to do many investigations. And of course, everybody wants to understand the evolution of the non-equilibrium, right? But if they are in this class of universality, we can try to come and understand and characterize even more the non-equilibrium state caused by this present in this turbulent cloud. Just to finish, more recently we did some very interesting thing that only happens in quantum fluids, is a spontaneous generation of turbulence. Basically what we do, we produce a very high charged vortex, in this case n equals to 4. So this vortex is a giant vortex in the middle of my cloud, and as I told you, it will decay. And then it will decay in tiny little single vorticity vortices. So this picture is a real picture of the cloud. You have a giant vortex and then decay to 4 tiny ones. And this is a phase imprinting type of technique. It's fully different from what I'm doing by shaking the condensate, okay? But we were able to observe the evolution of the system to turbulence. So we have a giant vortex. This is not turbulent at all. But because of this decay, the system evolved to turbulence. And now we are characterizing. I don't know if it's going to work. I hope it does, because that's a nice simulation showing the system to reacting the vortices that decay, evolving to turbulence. And we characterize this, we send it to be published, and then of course the referees ask us to do another 1,000 experiments to prove things. And that's what we're doing now, to answer questions and to be able to understand this spontaneous generation of turbulence in the quantum fluid. That does not happen in a cup of coffee or anything like this, because if you generate a giant vortex, it will decay. Will not will decay as a all. Will not decay in tiny vortices that can react and produce the turbulence. Well, I have been published papers, but we produce by invitation a few review papers. And if you are interested in knowing what we are doing, I recommend you these 2 reviews. I think it somehow put together, especially this one on the 2019, which is a more recent, and now, well, but the last year we were able to produce a lot of new things, but you can see publications in your homepage as well. This is the whole group. It's not everybody working in atoms. It's a combination of people working biophotonics and atom. And I should always acknowledge all my people, but also my collaborators. And for a while, we had a strong collaboration with Giacomo Ruati from Italy, Yukalov from Dubina, Barenghi from Newcastle, England, Tsubota from Osaka City University, Alex Fetter from Stanford, Robin Kaiser, Ipen, Handy Hewlett from Texas, Victor Romero from UNAM, and some other people local here like Edmir Santos. Well, my team here, my laboratory involves 3 different branches. I basically work in atomic physics and biophotonics, but there are other 6 faculties that are spread in different things. And well, since I'm giving this talk to the United States, there is a very famous phrase from an American writer that I've learned that people will forget what you said, people will forget what you did, but people will never forget how you made them feel. So I hope that you at least feel good with the talk, because then you're not going to forget me. Thank you very much.
Thank you very much, Vanderlei. Some questions. I guess it's 12. Some people may leave, but people are welcome to stay behind to ask more questions. Maybe let me.
Yes.
Okay. Maybe I start with a general question. This wave speckle, I think, is not. I mean, turbulent BC is an example of matter wave speckle, but there are other ways to create matter wave speckle.
Oh, no, of course. Yeah. I mean, it turns out that at the end, you see, Jane, we don't know exactly how is the evolution of the turbulence. Because, you know, we know the starting point and we know the ending point. We would like to know more the steps in between. I have a paper that was done together with Yukalov that he claims is the inverse Gibbel-Zurich type of effect. You start with vortices, you go to turbulence, you go to wave turbulence, and then if you keep putting energy, of course, you're going to destroy everything. You're going to end with a thermal cloud. And I'm trying to go and see step by step if we can identify the evolution of the turbulence. And but at the end of the day, if we don't keep pumping energy to destroy everything, right? If you keep pumping energy, you're going to destroy everything and end with a nice thermal gas. But if you don't do that, it seems that in some stage, you end by having those very big fluctuations, still a quantum system with big fluctuations on the amplitude and the phase. We introduced so many phases there, right? We don't know when we create the vortex, in what moment. So that is a big mass of amplitude and phases. And that is exactly the definition of the speckle field.
Yes. Basically, for example, you can load BC into a optical speckle potential, which is actually...
No. Yeah. But that is, you produce a random potential. And then you let the matter wave interact with that random potential. Mm-hmm. Yeah, I agree. But here is not what we did.
I understand. That's not what you did. Right.
Evolution of the excitations we put in the system. Yeah.
I'm just saying, if you do that, after a while, you can create what's called a granular BC with fluctuating phase and amplitude as well. So if you compare that system, which sometimes people also call that matter wave speckle, create that way, with your turbulent BC as a matter wave speckle, what's the unique feature that would happen in your turbulent BC that is not happening in a general matter wave speckle?
Yeah, well, but that's nice because you see, we are still characterizing the final stage of our turbulence. So my idea is to do the liberation. This paper that I published in the Proceedings of the National Academy of Science, it's only showing that by analyzing the speckle type of characteristics of the expanding cloud, we can characterize the statistics, right, of what's going on there, like they do with the speckle fields. And I can do that in different stages. This would be the idea.
Okay, thank you. Let's see.
One question or comment related to Young's question is that in the case you produce a granular BC, you somehow the scaling behavior, if you make an expansion, would probably likely depends on the speckle field you put in. But in the turbulent behavior, I think that probably depends on some microscopic physics in the BC, I guess.
Yeah, that's true. But you see, we are sampling different things here. One is looking the aspect of the density correlation. The other one is just looking to the momentum distribution in situ. This is what we're doing. When I look to the far from equilibrium aspect of it, I don't worry about the correlation. I just worry about how is the evolution of the momentum distribution.
Okay.
And everything is what's happening in situ. I'm picturing there. To see the speckle, I have to let the speckle characteristics, I have to let this propagate. It's exactly like a laser. If you don't propagate, you're never going to discover you have the structure there in the beam.
Mm-hmm. Any other question? So, is there any rigorous kind of a definition for turbulent BC? Is that important?
Oh, that's a very good. That's a very good question. You know, in classical fluids, people have a very, let's say, phenomenological way to define things. And that's the way they did. And they survived quite well.
In fact, I don't even know what is the official definition of a turbulent classical fluid.
Well, in classical fluids, they define it by looking the compromise between the flow, which is the flow and the viscosity. And they come with an empirical relation, that's the Reynolds number, and then there is another 100 type of adimensional quantities that more or less show the evidence of turbulence. The only thing that we have solid in turbulence is the Kolmogorov law. That is a symmetry that has in the problem that you can predict it. And, to solve the Navier-Stokes type of equation for the regular fluid is complicated. It's, people are still trying to understand everything there. You see, when you have a laminar flow, I'm talking about classical, and then suddenly those flow lines start to cross. That's the end of it, because the system can take a choice in going either, and then they start to create the classical vortices, right? And the system will stay a big mess. In the quantum domain, we believing in Feynman, we were focusing in the hydrodynamic type, which is the one based on the vortices. But still, if you look in the last few decades, there are many groups doing quantum turbulence in liquid helium, but they did not really evolve. I mean, they evolved, of course. We know much more than we knew before, but we still don't have an overall picture. Every time we see different things coming.
Okay. Any other final question? All right. If not, yes, maybe last question from you.
Thank you. So I have a question on the transition to the turbulent BC. So I think, as you mentioned, some kind of dissipation must be involved in such kind of transition. But it seems like in the turbulent BC, the quantum coherence is still preserved to some extent. So my question is, can a unitary time evolution of BC maybe not in an equilibrium state, maybe some after some quench, can such kind of BC translate to a turbulent BC?
Yeah, a quench. This is what I'm doing in the other experiment now. The other experiment that involved the sodium, I started by steering. So I had one of those nice devices that make a laser beam going around. And then you can produce vortices equal each other, all the same sign, positive circulation, all the momentum indicating the same direction. Now we're doing quenching, either in the interaction or in the potential. So I start with a potential like this, very shallow, and then I chop. And depending on this, I generate so many excitations that I can see equivalence. And then I probably will evolve to turbulence. And there is also the quenching on the interaction. you know, we could go and change the interaction suddenly, and the system find itself so far from equilibrium that many excitations will be generated, and you're going to evolve to turbulence. And then from there, the system, of course, will find ways to decay. It may take you forever, but it happens.
I see. So one can still understood it as some kind of unitary evolution, which is similar to the generation of quantum chaos. So the system
I think you're right. There are many connections, but at least in the system that we work, I don't know if in general turbulence is so broad. I could not say that everywhere it has to do with chaos, but I see that it may be, there are some connections. But even though this is, at the moment, you see, I expended basically 10 years finding, demonstrating, understanding, and now I think we are reaching the situation to show that turbulence in these systems is a special type of far from equilibrium. And now I hope to, you see, I did an experiment, did not show to you, which I see the system, I waited long enough. I see the alpha and beta coefficient, which characterize the proximity of these known thermal fixed points, evolving and coming back into zero, which means it's not there anymore. So I'm trying to find the time window in which the system preserves this kind of scaling behavior.
I see. Thank you.
Oh, thank you.
Great. Thank you, Vanderlei, for the talk and for answering all the questions. I really appreciate it.